Okay, so this is lecture 23 for the second lecture for our discussion on the transient simulation. And this is a part 1 scheduled for only for 20 minutes long, and after that I will make the part 2 covering the second part, so not covered in this part 1. So before starting the discussion about a transient simulation, so previously in the last lecture we have thought about how can we consider the time derivative term. If we have time derivative term, it can be obtained as just for example backward Euler method, like if we have f of a certain position r, then the position is fixed and only the time variable is changed, and this time difference delta t can be used to control the quality of your time derivative. That was backward Euler, and maybe you remember that instead of this backward Euler we have introduced second order method, Gear's second order method, and it showed better performance. But anyway, so we have thought about how can we discretize the time derivative operator. Wow, it's good, and now it's time to move to our device simulator. So now we have a device simulator. Then in the device simulator we have certain quantities like time derivative of our electron density and time derivative of our hole density. Those kind of terms can be easily discretized with this conventional way to discretize our time derivative operator. But today, before talking about that capability, we have to consider so-called mixed mode simulation capabilities, because in many cases our interest is not just laid on time dependent operation of a single MOSFET. For example, let's say this one. Here we have input voltage, and now we have a certain output current. If we are interested with those kind of situations, then yes, we can easily perform the time derivative. However, in many cases our usual use case is not like this. So instead of that, for example, we wanted to consider this kind of operation. So here we have V out and V in. We wanted to calculate the operation of this circuit, and what happens if we insert in, and what happens to our out voltage. So I'm not talking about voltage, the difference between voltage and current. It's not that so, but point is, in many cases, our ultimate interest is not laid on the single device performance, but the overall performance of a small circuitry made of device and lumped circuit elements. That is the point. So therefore, before talking about the transient capability, we must consider so-called mixed mode simulation capability, which enables the simulation of an entire circuit instead of a single device. So I just prepared the same example here. This is called a rectifier. So now up to now we have made a device simulator. So if we have this circuit, what can we do is actually simulate the DC characteristics of this D1. So when we have D1 and apply certain bias voltage to its anode, then we can calculate the DC current. So already you have done it. So x-axis is anode voltage, and if this is anode current, then what you get is actually something like this. Here we have, yes, this is you have obtained up to now. However, can we simulate this entire circuit having voltage source? Yes, that is possible. However, containing the resistor here. Well, right now it is not possible, and what we wanted to do is consider both of them simultaneously and get the solution. Of course, this circuit is not that difficult, so first of all, let's just qualitatively understand its behavior. So its behavior, okay, so pencil is stuck once again, so let's wait for a while. Okay, so its behavior is so simple. Here we have diode, which becomes quite much conductive when its bias voltage, anode voltage, is higher than for certain voltage range, for example 0.7 or 0.8. Beyond this level, then this diode becomes super not super, but highly conductive. So if we, for example, apply 2 volt to this V in, then what will happen? If this diode consume such kind of amount of voltage, then remaining voltage like 1.3 volt or 1.2 volt is just applied to this resistor. So think about this one. Now we wanted to introduce additional voltage 2.1 volt. Then what we have to do is additionally we have 0.1 volt additionally. Then between D1 and R1, which one will take this additional 0.1 volt? The answer is obviously R1 will take all of them, because when we have 0.1 volt difference in this R1, then increase of our resistor current will be simply given by this one. However, if we apply 0.1 volt to our D1, then what will happen? Then increase of D1 current will be given by current value of ID1 exponential times 0.1 volt threshold voltages. This exponential factor will be related to the increment of this one, of course -1, but that is quite high, so we can neglect it. So simply speaking, in this case, if our voltage is applied to the diode, then current is increasing too high, and when we apply 0.1 volt to the resistor, its current increase is just moderate. So what we have in reality is we have only small voltage applied to our diode, and all of the remaining voltage is just applied to the resistor. Since this delta is so small, what we can expect is, compared from this 2.0 volt to 2.1 volt, almost all of our applied voltage is just applied to our resistor. So simply speaking, what we can expect is V in and V out beyond a certain voltage. So after that, if we have a sufficiently high voltage, then what we can get is if you increase a certain voltage, for example 0.1 volt, and your output voltage is also increased by 0.1 volt, so there will be almost unit slope curve for your output voltage. Of course, this is made on the assumption of your D1 is highly conductive. In order to get such kind of a condition, D1 is highly conductive, at least you must spend 0.7 or 0.8 volt to your diode. So its behavior can be just visualized in this way. For first 0.7 volt or 0.8 volt, you just spend all of your applied voltage to D1. Once D1 is now activated and become highly conductive, after that, the additional voltage can be all consumed by this R1. So you will have conceptually very simple behavior. Of course, this one will have just unity slope. Slope is unity and this is just 0. So you will have just a piecewise linear behavior in rough sense in your rectifier. So what you expect is calculate this kind of behavior, but how can you automatically calculate this behavior out of your device simulator? Right now you cannot do that. Also, same difficulty can be experienced by just a sophomore level in EE department student. So what they learn in their microelectronics course is quite simple. One remedy is once they know the DC characteristics of the PN junction, then what they can do is they understand this one is an exponential function. After that, they apply the Kirchhoff's current law to this node. So simply speaking, incoming current from this diode is perfectly balanced by outgoing current by our resistor. This is diode current and this is resistor current. They are perfectly cancelled out or balanced. That is nothing but the KCL applied to this output node. So maybe if you are coming from E department, you remember that the graphical, so-called graphical approach to calculate this non-linear system. So they just say that this is diode voltage. Then that as a function of diode voltage, PN junction just looks like a certain exponential function. Its IV characteristics is exponential function. And here we have the linear dependence of current with respect to diode current taken from resistor. You can easily understand this one. After that, their cross-section meeting point here. So you can see that this one determines the operation point of this rectifier. So if we have a small input, then if we have a small input, then we will have just a small output. However, once we have large output, because this is too steep, let's say that, since this line is almost vertical, so even though we change our input voltage, but still we will have certain output voltage almost fixed to certain level. So be careful. X-axis in this graph is just the diode voltage. So diode voltage is almost fixed. Therefore, when you increase your input voltage, output voltage will be increased accordingly. So that was studied in the microelectronics course, but our main motivation is, instead of that, in this mixed mode simulation, we can consider not only semiconductor devices, but also circuit elements. So then it couples the device simulator, which consider internal physics of this diode or later transistor, and circuit simulator, which concerns about the balancing of current at circuit nodes. So mixed mode simulation simply means that the coupling between device simulator and circuit simulator. This is quite important uh, for considering the realistic case. So general implementation of this kind of capability would be involved. For example, let's consider a simple example for a voltage controlled oscillator. This is oscillator. So when you have this circuit and first introduce a certain small voltage noise or current noise into it, then it automatically oscillates and generates a certain signal. So in order to achieve this kind of thing, then your small circuit, this is a really primitive one. However, your simulator should consider two MOSFETs here and there, and two MOS varactors. Here you have another two. Varactor is nothing but just a variable capacitor, so it is realized by MOS system. Actually, you can think it as just a MOSFET whose source and drain are tied. So they are just a variation of MOSFET once again. And here you have also another type, P MOSFET here, and lumps elements like inductors are given here. However, in reality case, even these inductors are just decomposed into its internal resistance, capacitance, and inductance. Okay, so therefore, even though we are considering very primitive oscillator, however, even in this case, we have several devices, and in this case, we must pass the netlist. So if we have this kind of 1, 2, 3, 4, 5, 6, 7 circuit elements, there are lots of connectivity available from these 7 components. However, the netlist should describe, okay, this L1 and L2 are making a node, and this node is also shared by M3's drain terminal. Those kind of information should be given from our netlist file. That will be relatively long file, and that should be parsed in reality. However, implementation of this parsing capability would be quite involved. I think that this is a little bit beyond the scope of this course, mainly focused on device simulator. So in this course, we will consider really simple case. All register is attached to a terminal. So where can you find this thing? Yes, for example, you can consider this system as just a diode where uh, uh, a resistor is attached to its cathode. Then how about this anode? So in the case of anode, we can say that, okay, anode is also attached to a resistor. However, its resistance goes to 0. Very small resistance is attached. So then now you can think that this kind of system with this quite a simple approximation or assumption. So a resistor is attached to a terminal, then how can we consider this kind of a system? That is the main topic of our part 1. And since time is up, then I have to wrap up today's part 1, and maybe 30 minutes or 1 hour later I will continue to the discussion in part 2, but in the part 2 will be completely online, so please watch the recorded video later. So thank you for your attention, and I want to wrap up today's part 1. Thank you. And please note that I have just extended